Okay. So we are now live and doing some type of recording. Excellent. So today we're going to talk about programming. So is there any particular problem people want to program? And we'll do it live and hopefully it'll work.
Can we do that one? Want me to talk to that?
So we could try to do the football one, but we would have to know some things about expected scoring distribution. If you want, I am game to try that, and we would have to just put in some reasonable assumptions.
Is it all right
If we what?
type along?
Absolutely. Yes.
I want to do the first one on the second one.
Okay, which one was that?
Oops.
Yes.
Oh, the hoops problem?
Yeah.
Okay, let's start off with hoops. So we'll call it first to two. And so what kind of variables are we going to need for first to two? Yes.
A variable for each of the players.
Yeah, what variable?
Wins.
What wins? Close to wins.
Success.
Success. Now, do we really want to do first to two? Because after our success in doing first to two baskets, what might we have to do? First to n, right? So rather than doing first to two, let's just do first to n, and we'll have as the parameters n, p, and q. And then again, depending on what environment you use, it'll be slightly different. I love how Mathematica changes the formatting size. It somehow knows that I love spending my life adjusting the size. So whenever I do any coding, if I start something, I immediately end it. So I've started the module, I immediately end the module. So end of module. Then you want to put in some notation of what things is. You know, first to n baskets wins. First player gets basket with probability P, second with Q. And so by putting that in now, we've defined what our inputs are, so that when somebody's reading this code, they actually have an idea of what that is. That person who's reading the code could be you, months later, and you go, what did I mean here? And so I gave you, I think, a snippet of this in one of the lectures where we were doing regression, and I said at the end of the day, can you figure out what the hell I was doing? And without comments, it's often very difficult. So as we often do, let's do success. Will start to be 0, and this will be how often player 1 wins. And you might not want to do success because this is adopting a perspective that all we care about is player 1. We don't care about player 2. Screw player 2. I like player 1 because for me, I know player 1 is Bird. Bird is a Celtic. Player 2 plays for the Lakers. All right. So the next thing is going to be the big loop. I can't use n as my looping variable because n is the number of baskets. So I could do something different. So maybe I love using n for looping, so maybe I'll do b. First to b baskets wins. And that's actually nice because when I'm looking at it, b for baskets. So for n equals 1 and less than equal to numdo n plus plus, and then again we have decreased the size, and we'll see that there's another thing we need to fix as well. So now we've started a for loop, end of n loop. So I need to decide how many times I want to run the program. So I'll put a numdo over here. Okay. And so now, I've chosen a value of n, so I should probably initialize how many baskets player 1 has and player 2 has. If you wanted to, you could actually do this as a game with k players. And you might have, p might be an array with the different probabilities. So I'm going to just do this simple case of 2 players, but you should be thinking about modifying this more generally. So basket of 1 maybe is equal to 0, initializing player one's baskets. And then maybe basket 2 equals 0. And I will make all the code available afterwards. And so here's the thing. By writing it like this is a really good way to keep track of what's going on. So if I'm doing the loop on players, if my loop variable is 1, I will work with basket 1. Or you might want to say, well, rather than doing this, let's just call it B1 for player 1 and B2 for player 2. Which do people prefer?
I think with the bracket, the nice part is that if we go to like more than 2 players.
So the bracket is definitely easy if you go to more players. But what do people have as a preference? You know, today is about learning how to code. Do people want to do the brackets in the more general case, or do people want to do B1, B2? Brackets? Okay. Oops. Okay. So what we might do then is prob1 equals P, prob2 equals Q. Initializing player probability of success. By doing it that way, that's now better set up to deal with the different players. So far we haven't done any of the main code yet. We've just set up the things we want. And now we want to keep shooting. So what kind of loop what are we going to keep shooting until what happens? Somebody makes 2 baskets, except not 2 baskets, but not N, B, right? We keep changing things, right? But there's actually something we should do now that we have not done yet. It's disgraceful that we've been going for almost 10 minutes and we have not done this yet. It is not a line of code. What should I have done that I have not done yet?
Save it.
Save it, right? It's terrible to have gone this far. So just okay, so let's save it in the directory for this class. Let's call it first to n. Okay, so you should never go 10 minutes without saving. If you really want to be good, you should have your file name and a backup file name. Because what happens if the computer crashes while you're saving? You lose everything. Or you occasionally want to increase the file number so that if something was working and then it's no longer working on the new version, you can actually go back to something that's earlier. All right, so I think a while is going to be great here. While basket 1 is less than n, and what else must be true?
Basket 2 is also.
Right, and that's and. Oh, you're right, yes, thank you. Yes. So let's see if this will work. Initially, we're going to assume that you do not input, that it's the first to 0 baskets. You could put a line of code that basically says, if b equals 0, print you are an idiot. Okay, why would I have a line like that?
Test whether it goes into that.
Well, so what would it mean if b is 0?
Not with entering the right input.
Yeah. we're playing the game, the first to 0 baskets wins, right? So sometimes you actually put lines like this to let people know that they might have actually put the wrong input in. It's a really good programming technique to do something like that. We will assume that all of you are not idiots, and you're not going to play the first one to 0. This is not a very challenging game. Okay? Some games in life are not challenging. Chess, challenging. Go, challenging. First to 0, not challenging. War, the card game, not challenging. If you ever have to babysit the quiet contest, where you had that done to you? Wow. Okay. So when I was a kid, the older babysitter says, we're going to have a quiet contest now. We're going to see who can be quiet the longest. But what's nice is, when it's done to you, you can do it to others later. Right. So B is initially going to be positive. B is going to always be positive. So initially, basket 1 and basket 2 are both less than B. So we're going to enter the while loop. And we're going to stay in the while loop as long as both basket 1 and basket 2 are less than B. And as soon as one of them is greater than B, we're going to exit the loop. And one of the things that a lot of people made this mistake of in the problem is you had this notion of fairness, of letting player 2 get their last shot. Life is not fair. It sucks to be player 2. It's an extreme disadvantage. Right? And so as soon as player 1 gets the beef basket, game's over. As soon as player 2 gets the beef basket, the game's over. So the first thing we want to do is, let's let X will be random. So player 1 shoots. I could do all this in one line, but I'm doing it short. And I'll have Y equals random, so that'll be for player 2. And again, I could use arrays. It's actually slightly bad to do it like this, because what happens if this is the very last, if player 1 has B minus 1 baskets and gets a basket? Does player 2 need to shoot? No. So I actually calculate one more shot than I need to. Not a big deal. Why is it not a big deal? Because this is not a card problem, so there's no deal involved.
Because the game would be over.
Yeah, but I'm still doing extra work. My computer is running longer than it needs, so I'm doing one extra shot. Why is it not a huge deal that it's doing one extra shot? It's fast. The cost of one extra shot, if we're going to be simulating this a million times, and how many shots do we need before the game's over, the cost of one extra shot is probably not that much. You should do the code 2 different ways, and you'll see there's a negligible cost in runtime. For other things, there could be a significant cost in runtime. If the probability of P and Q are both very close to 1, then they might win very quickly, and then you're running a little bit longer. But in general, based on how many shots you have, it's really not a big deal. So now, if X is less than or equal to P, so what should happen if X is less than or equal to P?
Everyone should make a basket.
I'm sorry? Player 1 makes the basket. So then in this case, basket 1 equals basket 1 plus 1. But I might want to do more things here. Well, I'm not going to break it up in several different ways.
So instead of P, we should use prob.
Oh, yes, prob. Yes, thank you. So we should do prob 1. And now, if basket 1 equals B, End of if statement. So what should happen if this is player one's beef basket?
Success should be.
Good, so success should be increased by 1. So success equals success plus 1. Am I going to continue going through the while loop? No. In fact, I don't need to worry about breaking the while loop. Normally I would say break out of the while loop, maybe make basket 1 equal b plus 5, basket 2 equal b plus 5. I don't need to. I'm actually going to break the while loop at this point. Yes?
What does it mean, like x is less than or equal to 1?
So x is a random number. So randomly chooses a number uniformly in the interval 0, 1. And so if x is less than probable, well, what's probable 1? It's p. It's the probability of success. So think of p as 0.75.
So should that be greater than 1?
No, because p is the probability that we make a basket. So if p is 0.75, if I choose a random number from 0 to 1, anything from 0 to 0.75 should count as a win. So actually, I don't really even need all this big if statement. I don't need the begin and the end. I can actually just make this all just one line. Right? What happens if, now let's look at what happens for the next play. If y is less than or equal to probability 2, then what happens? Yeah, so then basket 2 should equal basket 2 plus 1. Do I need to worry about anything else? Do I need to worry about what happens if this is the beef basket for player 2? No, it's going to break out of the while loop. So I can put some comments. If x is less than or equal to p, player 1 made basket. So here, this would be if this is beef basket for 1, player 1 wins. Recording if player 2 made basket. And I can even put a comment, do not need to worry about breaking out of the while loop. And then let's save this because we haven't saved it in a while. Is there anything else we need to do for this loop for the specific value of n? Or does this solve the problem? And are we ready to run the program?
Print out.
Yeah, we need to print out. So years ago, I actually wrote a program to do something in additive combinatorics. And I needed to find a set that had a certain property. And typically, if you add a set to itself, you look at all pairs of sums, you will have more differences than sums. And this is a research project I've worked on with many Williams students over the years. Because addition is cumulative. 3 plus 5, 5 plus 3, they're the same. But 5 minus 3 and 3 minus 5 are different. But occasionally, you can find a set that has more sums than differences when you add. And the question is, well, what if you're dealing with sums of 3 or 4 sets? And so I wrote the code and I found an example of a set. And all I needed was to have one example and then I could construct infinitely many. The problem was I didn't output the set A. I outputted A plus A plus A. Oh, crap. There's more than one A that has the same A plus A plus A. What do?
Rerun.
You have to run the program again. You hope, please, dear Lord, please don't have me. I've just been extremely fortunate and lucky to have taken on my first day to get the result with
It was random.
because it was all random. Now, fortunately, there are so many things that work, within, a few minutes. I think I had another example. I did record what A plus A plus A was just in case. But you always want to think about what are you outputting? What are you recording? What are you saving to a file? Just because you don't need it now, future you might need it. And so you always want to think about what you're saving. So now we need, after the end loop, we want to print. So print player 1 wins. Then I'll do 100.0 times success divided by num2%. And then when you're running a program for the first time, the first time you run it, always choose small numbers. So let's do b is 1, let's do 0.5, 0.5, let's just do 4 iterations. Just because if it hangs up, you don't want it to be terrible. Oh, it's first 2 and just 1 n. But I need an extra t. It's first 2. Okay, player 1 won 100% of the time. It was the first to 1 basket. Are you surprised? Player 2 didn't even win once. What could I do? Run it again. So instead of doing 4, let's do 100 times. I now dropped to 61%. I believe the answer should be, if they're 50-50, I think it's 2/3. Now, the other thing you can do, which is really nice for something like this, is timing. And it will tell you how long it takes. So 0 point. What that means is this ran so fast, I can't even tell you how long it took. Let's make it 10,000. So 66.97, that's very much in line with our 2/3. And the time it took to run was 0.14 seconds. That's so small that I don't really trust it as a good measurement of how long the program takes, because you could have some just random fluctuations. If we run it again, it was 0.140, 140,625. Okay, so maybe that's pretty consistent, okay? So this should then maybe be about 1.4 seconds at 1.39. So you would expect that it should scale very nicely. And so if we do 1 million, we should be able to do 1 million in less than 15 seconds. And it should be pretty close to 66.6%. And you're using some of the basics we know about probability and central limit theorem. You can talk about what you expect the error to be. So it took 14.32 seconds and it was 66.7%. That's not too bad. If we were to do another 0, instead of taking 14 seconds, it would be about 2 minutes. Yes?
Why is the upper bound to the timing null?
Why is the what?
The upper bound to the timing null.
Yes.
It's null. Is there?
Oh, that's the second one. I'm not sure what the null means there. To me, the only part about it that I actually care about is the first part over here. That it took 14.32 seconds.
So it returns the time and the return result.
The return result.
Yeah.
And so this is not output. That would have been my guess. There's no return in this statement. So a lot of times when you write a program, you might write a program that is then used in something else. So I'll do an example of that after we finish this one. So any questions about how we would do this? So one thing you could do is you could add a little bit of a line, because this is taking time. I'm getting impatient. I need immediate satisfaction. I'm a product of 21st century America. I'm not used to waiting. Screw this. I'm going to do something else. I'm going to abort the program. What would be terrible for me to abort the program? It was almost done, right? So I want to know how close I am. So what I might do is the following. I'll do if, I'll do mod. All right, so
I looked online and it says if you click on the column on the right and then you set the size and it should permanently.
oh, okay. Well, thank you. I will try that. Oops, I think that's bigger than the size I was using. Okay, so it's still running. So for mod, I think the way mod works is the number is first and then what you want to mod it by is second. So what I'll do is I'll look at n. Oops. And then I will look at numdo divided by 10. And then if that equals 0, print we have done, then it'll be 100.0 times n divided by numdo %. So this will give me some idea of how much we've done. So at this point, it feels like it's been 2 minutes. Right? I only added one more 0. Okay, it just finished. Right. 66.669. Right. That's not bad. We're really seeing the 2/3. And now what I'll do is I will take this and I'll put it over here. I'll only do 1 million. So every 15, well, it should have printed out something by now. So let's do mod 12. So I'm not sure why it didn't print that. Oh, I know why. I don't think I recompiled this code. Okay, now it's saying that there's an error somewhere. So, right, so something happened over here. And this is why you should have different versions saved.
Maybe the closing comment the same. I'm not sure why it would be the same. Like the friends and the star. Or yeah.
Right, so somehow these seem to have changed.
By the highlighting, it looks like it's.
Okay, now it's working. Now it's printing out, the different percentages that it's doing. But this is a great example of why you want to have a different file name and just change them periodically, so that when something like this happens, you can just go back to something that works. Okay. Any questions about this code? So, based on how much time we have left, let's just do a very simple benefits law of digit bias. This is a topic we might do later this semester. I've done a lot of research on this. So we will do first digit. And I will use your comments. So please send me an email for telling me that I can do this and make it global, because that is very useful for me to know. So what I want to do is I want to detect what is the first digit of a number. And Benford's law says that in many data sets, you have a first digit of 1 approximately 30% of the time, and a first digit of 9 only about 4.5% of the time, 4.6% of the time. So if you write a number, how would you get its first digit? So you want a little bit of a theory. So we'll assume our number is positive. So we don't have to worry about, is it negative? We don't have to worry if it's complex valued. We can write our number as a significand. So this is something between 1 and 10 times 10 to an integer. And we don't care about that integer part. So what we can do is we can take the log of our number base 10. We don't care about the integer part, so look at this mod 1. And then raise 10 to this. And then just take the floor of this. And I think that should work. So the first thing, I sometimes like to have a second window open. The log of 100 base 10 is 1/2. The log of 10, 100 is 2. Okay, so when you do the logarithm, the first piece is your base and the second piece is the number. So it's nice to just have a second window open to test something like this. So I would want the log base 10 of my number. Then I want to look at it mod 1. And then you might be worried, does mod work for fractions? Let's do square root of 2 times 1.0. And so it does give me the fraction part, good. So now that I have this, I take 10 to that, I believe. And then I take the floor. So let's do first digit of 1000 pi. What should that be? Okay, not surprisingly, it's 3. Let's do 25 squared. 25 squared should be 625. So you always want to just test things and see if it works. So what we can do is we can write a short program now that will use this as an input. So we'll call it Fibonacci Benford test. And we'll just do some number. And then we'll save things. Okay. So again, I'll start off with a module. End of module. Okay, and now what I want to do is I'll initialize the percentages to be 0. So for d equals 1, d less than equal to 9, d plus plus, digit of d is equal to 0. I can record the benefit probabilities for d equals 1, d less than equal to 9, d plus plus. Benford prob of d is the log base 10 of 1 plus 1 divided by d. And if I want to, I'm just saving a little bit of time of not putting in comments now because we're down to about 10 minutes. I could have had this as just one d statement and just done both initializations all at once. That's absolutely fine. And so what I want to do now is I want to start calculating the digits of the first of the Fibonacci numbers. So there's a couple of ways you can do this. We have an explicit formula for the Fibonacci numbers. So we can just use that, or we can calculate the Fibonacci numbers as we go. So if we want to calculate the Fibonacci numbers as we go, we need to save some previous numbers. So we'll count the Fibonacci numbers as 1, 1, 2, 3. Right? So the first Fibonacci numbers, the first two numbers are going to have first digit of 1. So what I'll do now is I'll say digit of 1 is equal to 2. I'm going to initialize it from the first two ones. From the first two ones in the Fibonacci sequence. Now I will do current is equal to 1, previous is equal to 1. And what I'm always going to do is I'm going to just save the last two Fibonacci numbers, and from that I can calculate the next. So I'm going to have my main loop. So for n equals 1, n less than equal to num do, n plus plus. End of n loop. And now next is going to be current plus previous. And that's the next Fibonacci number. And so what I'll now do is I'll let D is going to be first digit of next. And then I will do digit of D equals digit of D plus 1. You could have made this a little bit more compact, but I really want to show what's going on. And so now, what do I need to do? So I have next, current, and previous. And I just made next equal to current plus previous. What do I need to do now? Update. So what gets updated first? So what should I assign to current? So current should now be next. And what should previous be?
Probably assign previous to current.
So I should do this one first. So order matters. Right? So what we're going to do is now previous equals current. And then current equals next. And that just saves the last two values. And I believe that's all we need to do. We need to print, right? So for D equals 1, D less than equal to 9, D plus plus, print theory equals, and then I'll do 100.0 times nth prob of D, and observe 100.0 digit D, and then we have to divide that by num do, I believe, because it's counting how many successes we have. So I hope that is all we need to do. So we'll do timing, and then we'll do Fibonacci Benford test. Let's just do 10 numbers. Okay. So let me see if I can perpetually make this larger.
Oh, so I looked online for a better way to do it.
Mhm.
If you go to Window,
Okay.
and then magnification, and then like percent, then it changes the whole document.
I see.
Yeah, so that's probably the best way. Then you don't have to like.
Right.
Change it.
Ah, excellent. So now over here, I don't really like the output because it says we observe for, oh no, okay, these are the percent. It's summing to more than 100%. Oh, it's summing to more than 100% because we have those two values in here, right? We have to do num do plus 2. right? Because we initialized to include 2 values in the beginning. So let's just do 8 things here. Good, and that's 100%. So with just a little bit of data in the beginning, just the first 10 Fibonacci numbers, we have 3 numbers that start with a 1. 1, 1, 2, 3, 5, 8, 13. Fine, not bad. We have 2 that start off with a 2, and it should have been 17%. But some of the lower values look pretty bad. So this will just record the values of the D's that we're looking at. We didn't get any 6s or 7s or any 4s or any 9s. Are you sad? How sad? Should I kick up the dust in frustration? Why are you not surprised with this result?
10 numbers.
Yeah, we're using 10 numbers, and they're the beginning 10 numbers, so the pattern may not have really sunk in yet. Let's go up to 98, so that's 100 numbers. And then what we can also do over here, no, I won't bother doing this right now. So this is running really fast. So let's do the first 10,000. Do those numbers look pretty good? Yeah. What we could do is, we should actually record this. Let's give this a name. Observed D. Okay. So for D equals 1, D less than equal to 9, D plus plus, observed D equals this. And the reason I want to do this now is I can then say, and difference is 100.0 times nth prob of D minus observe of D. That's bad. Because over here I included the 100 in the definition. So now, and again, this is all how do you want to display the data? You can do histograms and whatnot as well. There's a lot of graphing capabilities you have. But when you look at this, the difference in percentages is not that bad. Now this took about 1 second. So how long should it take if I put in, took 1.1 seconds? How long do you expect this to take? It was 1.18, call it 1.2 seconds. But how long should it take to do 10 times as much? So one possibility is 12 seconds. I don't think it's going to take 12 seconds.
I'm really embarrassed.
The numbers are getting bigger. So this is not going to be a nice linear increase. In the basketball game, I had no concerns about going up a factor of 10 or a factor of 100. I had a great idea of how long that was going to take. For something like this, the small numbers in the beginning are much easier to deal with when the numbers get larger. And you go, come on, we're just adding numbers. Well, about how large is the 10,000th Fibonacci number? It's very large. It's approximately 1 over root 5, the golden mean, which is 1 plus root 5 over 2 to the nth. And you subtract off 1 over root 5. When n is 10,000, and this number is less than 1, I'm really not concerned about a number less than 1 by a sizable amount raised to the 10,000th power. Goodbye. I don't care. So for somebody who has a computer open, you want to estimate what that is.
Oh.
I'm sorry?
It's a very big number.
It's very big. This is why it would be nice to have the line of code that prints out how far we've done.
For 10,000, it's like 10 to the 2,000.
So Mathematica is working with 2,000-digit numbers. And it did that in less than 2 minutes. It took it about 88 seconds. And you can see the probabilities are fairly good. Fibonacci number is actually one of the best fits to benefits law database. Absolutely amazing how good of a fit this does. But you can see we really should have our line of code that lets us know how much we've done. Because for something like this, it's frustrating. Now, if I try over here and just write next, it has next still stored in memory because it calculated it. So this is the last of the numbers. And so if you want to know what this is either the 10,000th to the 10,001st Fibonacci number, you can just hit pause as it's being recorded. And there you go. Or what you could say is, screw that. I want to get just some sense of just how bad is this. So let me do the log base 10 of this.
Wait, actually, I think we're dealing with 100,000.
Oh, sorry, the 100,000. Sorry, yes. Oh, so if I gave you 10,000, yes, sorry. So this is roughly 10 to the 20,898. So in terms of just, let's put this in perspective. How many letters are there in a typical word? 5, and then one blank space is 6. So there's about 6 characters in word. How many words on a line? I want to say 10 words, 12 words, 15 words. 15 times 6 is 90. Call it 100 characters a line. So if it's 100 characters a line, if this is around 21,000, this is about 200 lines of text. So it's on the order of a page. And if you looked at the size of it, yeah, it kind of seems like on the order of a page or two. You want to get a sense of just how big is it that you're talking about. It's on the order of a page. And if you went further, you would get some sense of, oh my God, just how bad is it going to be? All right. So I think this is